Welcome to Spaceverse, your portal to cosmic adventures. Telescopes have been our windows into the cosmos for centuries, but Earth-based models, while powerful, face limitations in capturing light compared to the advanced space telescopes of today. President Biden's unveiling of the first James Webb Space Telescope image signaled a new era for astronomy, showcasing an observatory capable of probing farther into the universe than ever before. Unlike previous telescopes, the James Webb is equipped to observe infrared light, allowing it to pierce through cosmic dust and reach deeper into star-forming regions, distant galaxies, and exoplanet atmospheres. This capability lets scientists study phenomena that were previously out of reach and opens new avenues to explore our place in the universe. Recently, JWST turned its attention to an exoplanet orbiting a star 120 light-years away, unveiling potentially groundbreaking insights. The planet, K218b, orbits within its star's habitable zone, where conditions might allow liquid water to exist. Initial observations revealed the presence of carbon-based molecules like methane and carbon dioxide in its atmosphere, hinting at a high aquatic environment. This discovery suggests that K218b could host vast bodies of liquid water beneath a hydrogen-rich atmosphere, making it unlike anything seen in our solar system. Weighing 8.6 times more than Earth, this mini-Neptune challenges our understanding of planetary types and may expand the criteria we use to assess a planet's potential to support life. With its remarkable capabilities, JWST has taken us a step closer to identifying worlds that might be suitable for life, adding weight to the possibility that we aren't alone in the cosmos. Observing atmospheres for carbon-bearing molecules is key to identifying potential life-supporting environments, making the telescope's findings on K218b a major milestone in the search for habitability beyond Earth. K218b is a fascinating exoplanet located 120 light-years away in the constellation Leo. It orbits a cool M-type red dwarf star called K218, positioned within the star's habitable zone, a region where temperatures may allow liquid water to exist on the planet's surface. This habitable zone placement alone makes K218b intriguing, as liquid water is considered a crucial ingredient for life as we know it. One of the unique characteristics of K218b is its size, which falls between Earth and Neptune. This sub-Neptune size range is notably absent in our own solar system, which has either small rocky planets or large gas giants. Planets like K218b, with radii 2 to 4 times that of Earth, have atmospheres and possibly interior compositions that we don't yet fully understand. Scientists are still working to understand how these high aquatic worlds, or ocean worlds, may form and what conditions might prevail within their atmospheres and potential water layers. Recent analyses of K218b's atmosphere have sparked intense scientific interest. Using the James Webb Space Telescope, researchers detected the presence of carbon dioxide and methane, both of which are considered indicators of potentially life-supporting chemistry. Interestingly, ammonia, a molecule commonly associated with non-aquatic, gas-dominated worlds, appears to be absent, which might suggest that K218b has a water-rich environment below its hydrogen-rich atmosphere. This layering could mean that K218b has a deep water ocean, possibly capped by thick atmospheric clouds, much like hypothetical models of ocean planets. One of the most exciting aspects of K218b's atmosphere is the potential presence of dimethyl sulfide, a molecule that on Earth is exclusively produced by living organisms, especially marine microorganisms like plankton. Though the current data is not definitive, future observations by the James Webb Space Telescope may provide enough evidence to confirm or refute the presence of DMS in the atmosphere. If confirmed, it would be a groundbreaking finding, as it would suggest that biological processes similar to those that occur in Earth's oceans might be possible on K218b. K218b's complex and potentially life-supporting environment could greatly expand our understanding of habitable worlds, particularly those that differ significantly from Earth. Its study may lead to a new category of potentially habitable planets that include ocean worlds with thick, hydrogen-rich atmospheres, offering valuable insights as we continue the search for life beyond our solar system. While K218b's atmosphere contains carbon-bearing molecules, and it lies in its star's habitable zone, this doesn't necessarily mean it can support life. The planet's radius is 2.6 times that of Earth, and it's believed to have a dense core of high-pressure ice, similar to Neptune, but with a thinner hydrogen-rich atmosphere and potentially an ocean surface. For these high aquatic worlds, large bodies of water are expected, but it's possible the water could be too hot to support life or even remain in a liquid state. We've obtained the most detailed spectrum of a habitable zone sub-Neptune so far, allowing us to identify the molecules in its atmosphere, Subhajit Sarar from Cardiff University said. This breakthrough was achieved by studying how light from K2-18b's host star filters through the exoplanet's atmosphere during its transit. Because K2-18b is a transiting planet, it periodically dims the light of its star as it passes in front. Discovered by NASA's K2 mission in 2015, each transit allows a small fraction of the star's light to pass through the planet's atmosphere before reaching telescopes like the James Webb, leaving telltale spectral fingerprints that reveal the composition of its gases. Looking ahead, the research team plans to use Webb's mid-infrared instrument spectrograph for further observations, hoping to verify these initial findings and gain deeper insights into K2-18b's atmosphere and climate. The discovery of life on a habitable exoplanet would transform our understanding of humanity's place in the cosmos. According to Madhu Sudan, the James Webb Space Telescope has detected water in various locations across the universe. And now, JWST has identified complex carbon-based molecules resembling haze or smoke in a distant galaxy, pushing back the record for detecting such molecules by nearly 1 billion years. This means we're now seeing the oldest known instance of complex organic compounds in the universe, a thrilling yet somewhat daunting revelation that reshapes our cosmic perspective. What does this mean exactly? These components were found in an early galaxy that formed when the universe was only about 10% of its current age. That's the first key takeaway. On Earth, similar carbon-based compounds called polycyclic aromatic hydrocarbons are found in smog, coal, and oil. But this discovery is significant for another reason. As lead astronomer Justin Spilker explains, these aren't simple molecules like water or carbon dioxide. They're enormous, squishy compounds made of hundreds or even thousands of atoms, molecules that, according to existing models, shouldn't have formed so soon after the Big Bang. Yet here they are, evidence that the early universe was capable of creating surprisingly complex structures. To grasp the timeline, remember that we live in a universe about 13.8 billion years old. The light Webb has detected from this distant galaxy began its journey just over 1.5 billion years after the Big Bang. Thanks to JWST, we've not only glimpsed the early universe, but also set a new benchmark, detecting complex organic molecules far earlier than previously thought. This achievement sheds fresh light on the building blocks of life and reveals an era in cosmic history that we're only beginning to understand. Imagine if we could delve even further back in time to moments preceding the Big Bang. What would we find if we encountered not only the faint glimmers of light from the universe's birth, but also a thriving complexity of molecules that existed before our current understanding allows? Such a discovery would not merely add a new chapter to the annals of science, it would fundamentally reshape the foundations of cosmology, challenging and expanding our knowledge of how the universe evolved and how life itself may have sprung into existence. We've long speculated about the ingredients necessary for life, yet finding traces of these complex molecules in the universe's earliest history would suggest that life's building blocks might have been present far earlier than we ever thought possible. This intriguing possibility brings us to a revolutionary development. Previous telescopes were able to detect organic molecules across vast cosmic distances, confirming their presence in galaxies far away. But with the James Webb Space Telescope, we're experiencing a leap in capability. Webb's unprecedented sensitivity not only allows us to detect these molecules, but also enables us to map their exact distribution within galaxies. For the first time, we can witness the precise arrangement of complex organics in early galaxies, adding a new layer to our understanding of cosmic structure and evolution. One particularly remarkable case is SPT 0418-47, an ancient galaxy that has come under Webb's watchful gaze. This galaxy offers an astonishing insight. Its organic molecules are spread in a patchy, uneven manner. This curious distribution is still unexplained, suggesting that galaxies in the early universe, even when only a tenth the age of our Milky Way, already held mysteries and complexities that defy current theories. Notably, SP0418-47 was both vast and chemically rich, containing as much carbon and oxygen, key elements for life, as our own galaxy today. The universe, in all its vastness and complexity, never ceases to astonish. As human beings driven by curiosity, every step into the cosmic unknown pulls us closer to understanding the mysteries of existence. With each breakthrough, Webb transforms our view of the cosmos, not just illuminating distant galaxies, but reshaping our perception of the universe's potential for life and evolution. Each discovery Webb delivers isn't just an addition to our knowledge, it's a profound step forward, revealing the universe in all its intricate wonder, one piece at a time. And that's it. Thanks for tuning in to Spaceverse. Today, we explored the potential of complex organic molecules existing before the Big Bang with insights from the James Webb Space Telescope. By mapping these building blocks in ancient galaxies, we're uncovering the universe's mysteries. Join us next time as we continue our journey through the cosmos. Keep looking up, the universe has endless surprises.